Testing, can you hear me? Testing again, can you hear me? All right, so I'm going to be learning about computer architecture again. Last stream, I was learning about the pipelining stuff. I was learning about interrupts and handlers, how they implement the interrupt in the pipeline. This time, I'm going to be learning about performance metrics. Let us discuss the performance of our pipeline processor. We first need to define the meaning of performance in the context of the processor. Most of the time, when we look up the specifications of a laptop or a smartphone, we are inundated with a lot of terms such as the clock frequency, RAM, hard disk size. Sadly, none of these terms are directly indicative of the performance of a processor. The reason that the performance is never explicitly mentioned on the label of a computer is because the term performance is rather vague. The performance of a processor is always with respect to a given program or a set of programs. This is because processors perform differently with respect to different programs. Given a program P, let us try to quantify the performance of a given processor. We say that the processor A performs better than processor B if it takes less time for P to execute P on A than on B. Thus, quantifying the performance with respect to a given program is very simple. We measure the time it takes to run the program, then compute its reciprocal, this number. Can be interpreted to be proportional to the performance of the processor with respect to the program. Let us first compute the time tau it takes to run program P. The number of cycles per second is the processor's clock frequency. The average number of cycles per instruction is known as the CPI. And its inverse, number of instructions per cycle, is known as the IPC. Instructions per cycle. The last term is the number of instructions abbreviated to number of instructions. Know that this is the number of dynamic instructions, or alternatively, the number of instructions that the processor actually executes. Note that it is not the number of instructions in the program's executable file. Yeah, the seconds per cycle. Cycle per seconds times instruction. CPI times number of instructions divided by the frequency. Pipeline data path with support for exceptions. So what was all this then? Oh, this is for switching the context, for storing and restoring the context. All the register, the contents of the register, they go to where the stack pointer is pointing to. Okay. The static instruction, the binary or executable of a program contains a list of instructions. Each such instruction is a static instruction. The dynamic instruction is the instance of a static instruction which is created by the processor when an instruction enters the pipeline. We can now define the performance P as the quantity that is inversely proportional to the time tau. Equation 10.3 is known as the performance equation. So performance is proportional to IPC times F divided by the number of instructions. Wait, this is the inverse of seconds. Okay. We can thus quickly conclude that the performance of a processor with respect to a program is proportional to the IPC and frequency and inversely proportional to the number of instructions. Let us now look at the performance of a single cycle processor. Its CPI is equal to 1 for all instructions. The performance is thus proportional to F divided by number of instructions. This is a rather trivial result. It says that we can increase the frequency. A single cycle processor keeps getting faster proportionally. Likewise, if we are able to reduce the number of instructions in our program by a factor of x, then the performance also increases by a factor of x. Let us consider the performance of a pipelined processor. The analysis is more complicated and the insights are very profound. Performance of an ideal pipelined processor. Let us look at three terms in the performance equation and consider them one by one. Let us first consider the number of instructions. The number of instructions in a program is dependent on the intelligence of a compiler. ADD Smart Compiler can reduce instructions by choosing the right set of instructions from the ISA and by using smart code transformations. For example, programmers typically have some code which can be categorized as dead code. This code has no effect on the final output. A smart compiler can remove all the dead code that it can find. Another source of additional instructions is the code to spell and restore registers. Compilers often perform function inlining for very small functions. This optimization dynamically removes such functions and pastes their code in the code for the calling function. For small functions, this is a very useful optimization since we are getting rid of the code to spell and restore registers. There are many more compiler optimizations that help in reducing code size. The reader is referred to Aho at 2006. Okay. For a detailed discussion on compiler design. For the rest of the section, we shall assume that the number of instructions is a constant. Let us exclusively focus on the hardware aspect. Let us assume an ideal pipeline that does not need to insert any bubbles or stalls. It will be able to complete one instruction every second and thus will have a CPI of 1. Let us assume a program containing n instructions and let the pipeline have k stages. Let us compute the total number of cycles it will take for all the n instructions to leave the pipeline. Let the first instruction enter the pipeline in cycle 1. It leaves the pipeline in cycle k. Wait. Shouldn't it be like cycle 5 because there are 5 stages? Or maybe like division or multiplication, it takes multiple cycles. Maybe because of that. Henceforth, one instruction will leave the pipeline every cycle. Thus, after n-1 cycles, all the instructions would have left the pipeline. The total number of cycles is therefore n plus k minus 1. The CPI is equal to n plus k minus 1 divided by n. Note that the CPI tends to 1 as n tends to infinity. Let the maximum amount of time that an instruction takes to finish its execution on a single processor be T max. This is also known as the total amount of algorithmic work. We are ignoring the delays of pipeline registers while computing T max. Now let us divide the data path into K pipeline stages. We need to add K minus 1 pipeline registers. Let the delay of a pipeline register be L. If we assume that all the pipeline stages are balanced, do the same amount of work and take the same amount of time, that the time that the slowest instruction will take to finish its work in a stage is equal to T max over K. The total time per stage is equal to the circuit delay and the delay of a pipeline register. T stage is equal to T max divided by K plus L. Now the minimum clock cycle time has to be equal to the delay of a pipeline stage. This is because the assumption while designing a pipeline is that each stage takes exactly 1 clock cycle. We thus have the minimum clock cycle time or the maximum frequency equal to 1 over F or T max divided by K plus L. Let us now compute the performance of this pipeline and make a simplistic assumption that performance is equal to F divided by CPI, because the number of instructions is a constant, which is N. So, wait. So the maximum amount of time that an instruction takes to finish its execution on a single cycle processor is T max. Algorithmic work. We need to add K minus 1 pipeline registers. Let the delay of a pipeline register be L. The total time per stage is equal to the circuit delay plus the delay of the pipeline register. Let me think about this. So the data path has K pipeline stages. It takes T max time to fully complete it, to go through all the stages. So one stage is T max divided by K, but also we should add the delay as well. Delay of a pipeline register BL. Now the minimum clock cycle time has to be equal to the delay of a pipeline stage. This is because the assumption while designing a pipeline is that each stage takes exactly 1 clock cycle. We thus have a minimum clock cycle or a maximum frequency equal to, so minimum clock cycle or maximum frequency is T max divided by K plus L. So performance is F divided by CPI. Wait, data performance was, yeah, never mind. F divided by CPI. And now we have, instead of F, we are writing 1 over T max divided by K plus L. That is this equation over here. We are dividing that by N plus K minus 1 divided by N. That is this equation over here. Simplifying it will give us this. Let us try to maximize the performance by choosing the right value of K. They're using derivatives. And K ends up being N minus 1 T max divided by L. Equation 10.8 provides a theoretical estimate of the optimal number of pipeline stages as a function of the latch delay, the total algorithmic work, the number of instructions. Let us gauge the trends predicted by this equation. The first is that as we increase the number of instructions, we can afford more pipeline stages. This is because the startup delay of k cycles get nullified when there are more instructions. Secondly, as we increase the amount of algorithmic work, we need a deeper pipeline. More is the number of pipeline stages, less the amount of work we need to do per stage. We can thus have a higher frequency and a higher instruction throughput. Lastly, the optimal number of stages is inversely proportional to root L. As we increase the latch delay, we can start wasting more time inserting and removing data from latches. Hence, it is necessary to adjust the number of pipeline stages with the latch delay. The latches are very slow. We need to reduce the number of pipeline stages also such that we do not waste time in adding or removing data from pipeline latches. Sadly, in ideal, a pipeline does not exist in practice. This means that they do not have a CPI equal to n plus k minus 1 divided by n. Almost all programs have dependencies between instructions, and thus it becomes necessary to insert bubbles in the pipeline. Inserting bubbles increases the CPI from the ideal CPI computed in equation 10.4. From the ideal CPI computed in equation 10.4. Equation 10.8 provides us with an interesting insight. However, the reader needs to note that it is hypothetical. It predicts the optimal number of stages approaches infinity for very large programs. This is unfortunately not the case in practical scenarios. Performance of a non-ideal pipeline. We need to incorporate the effect of stalls in the CPI equation. Let us assume that the number of instructions is very large. In the ideal CPI, the CPI ideal, in our case, CPI ideal is equal to 1. We have CPI is equal to CPI ideal plus stall rate times stall penalty. Assume that the ideal CPI is 1. Assume that 10% of the instructions suffer a load use hazard. 20% of the instructions are taken branches. Find the CPI of the program. We need to insert 1 bubble for a load use hazard and 2 bubbles for a taken branch. Thus, the average number of bubbles that we need to insert per instruction is equal to 0.1 or 10%. So 0.1 and then 20% to 0.5. That's the stall rate, right? No, stall rate is this 10% and times it by stall penalty, which is we are taking up 1 stage, right? 1 clock cycle. Compare the performance of 2 programs P1 and P2. Assume that the ideal CPI for both of them is 1. For P1, it's 10% of instructions have a load use hazard and 15% of the instructions are taken branches. For P2, 20% of the instructions have a load use hazard and 5% of instructions are taken branches. CPI for P1. So the penalty is 1 cycle. Sorry, this is the what is the CPI ideal? But the penalty is 1, 10% of the time, and the penalty is 2, 15% of the time. We get 1.4 here and 1.3 for the second one. CPI P2 is less than the CPI P1, hence P2 is faster. Final CPI is equal to the sum of the ideal CPI and the number of mean stall cycles per instructions. The mean stall cycles per instructions is equal to the product of the average stalls average stall rate per instruction multiplied by the average number of bubbles that we need to insert per stall. The stall rate term is typically a function of the nature of dependencies across instructions in a program. The stall penalty term is also typically dependent on the design of the pipeline and its forwarding paths. In our case, we need to stall for at most one cycle for a raw hazard, for 2 cycles for taking branches. However, pipelines with more stages might have different behaviors. Let us now try to model this pipeline mathematically. We assume that the stall rate is dependent on the program and the stall penalty is proportional to the number of stages in a pipeline. This assumption is again not completely correct. However, it is good enough for developing a coarse mathematical model. The reason we assume that stall penalty is proportional to the number of stages is because we assume that we create deeper pipelines by essentially splitting the stages of our simple pipeline further. For example, we can pipeline the functional units. Let us assume that we divide each stage into 2 substages. Then we need to stall for 2 cycles on a load use hazard and stall for 4 cycles for a taken branch. Let us thus assume that CPI is equal to n plus k minus 1 divided by n plus RCK, where R and C are constants and k is the number of pipeline stages. R is the average number of stalls per instruction. That's the stall rate. What is C? C is the stall penalty. K is the number of pipeline stages. We assume that stall penalty is proportional to K, where C is the constant of proportionality. Stall penalty is proportional to K, and so we are writing it as stall penalty is equal to Ck, where C is the constant of proportionality. But I do not understand. CPI is equal to n plus k minus 1. Let me see how they got this equation again. So it takes k cycles for instruction to complete. N minus 1 cycles, all the instructions would have left the pipeline. There are n instructions, n minus 1. In n minus 1 cycles, all the instructions would have left the pipeline. Should it in n minus 1 cycle, like the last instruction should enter the pipeline, right? All instruction, the total number of cycles is therefore n plus k minus 1 n minus 1 plus k divided by n. The cycles per instruction is n plus 1, n plus k minus 1 divided by n. Okay. Now they're using it over here, but adding it with RCK. R is the average number of stalls. And this is the CK is the stall penalty. We thus have P is equal to F divided by CPI. Okay, let me see what they're doing. Okay, now we need to maximize this, minimize the denominator with respect to k. K, we go here and we approximately end up here. Equation 10.11 is more realistic than equation 10.8. It is independent of the number of instructions. The implicit assumption is that the number of instructions tends to infinity, because in most programs we execute billions of instructions. Akin to equation 10.8, the optimal number of pipeline stages is proportional to root Tmax and inversely proportional to root L. Additionally, K is proportional to 1 over divided by RC. This means that as a penalty for a stall increases, the number of stall events per instruction increase. We need to use less pipeline stages. Let us now find the performance for the optimal number of pipeline stages. In equation 10.10, we assume n tends to infinity, thus n plus k minus 1 divided by n goes to 1. Hence, we have P ideal. Well, how did they get P ideal from? So P ideal is 1 over T max divided by K plus L times it by 1 plus RCK. You have no idea what's going on in here. Equations, implications of equation 10.11 and 10.12. 10.12 is this one, right? Where P ideal is this. Now, how did they get this equation? Did I miss something before? P Implication 1, the crucial implication of these results is that for programs with allotted dependencies, you should use processors with fewer pipeline stages. Inversely, for programs that have high IPC, we should use processors that have deeper pipeline. Wait, hold on. Implication 2, let us compare two versions of our pipeline. One version uses interlocks for all dependencies, and the other uses forwarding. For a pipeline with forwarding, the stall penalty is much lower. Consequently, the value of the constant C is smaller in the case of the pipeline with forwarding turned on. This means that a pipeline with forwarding ideally requires more pipeline stages for optimal performance. As a general rule, we can conclude that as we increase the amount of powering in a pipeline, we should make it deeper. The optimal number of pipeline stages is directly proportional to T max divided by L. If we have faster latches, we can support deeper pipelines. Secondly, with the progress of technology, T max divided by L is not changing significantly because both logic gates and latches are getting faster. Hence, the optimal number of pipeline stages for a processor has remained almost the same for at least the 5 years. The last 5 years. As we increase L, R, C, and T max, the ideal performance goes down. As per equation 10.12. The latch delay can be a very sensitive parameter, especially for processors that are designed to run workloads with few dependencies. In this case, R and C will have relatively few small values, and equation 10.12 will be dominated by the value of the latch delay. What is this? Cancel. Why does Dropbox open? I connected my phone to my laptop and then Dropbox opened for some reason. Find the optimal number of pipeline stages for the following configuration. T max divided by L is equal to 20, R is 0.2 and C is 0.6. So we use 10.11, right? 20 divided by 0.2 times 0.6. We get 13. Consider two programs that have the following characteristics. So the load fraction is 0.4, branch is 0.2, over here it's 0.3 and 0.1, and the ratio of taken branches is 0.5 here and 0.4 here. The ideal CPI is 1 for both the programs. Let 50% of the load instructions suffer from a load use hazard. Assume that the frequency of P1 is 1, the frequency of P2 is 1.5. Here the units of frequency that are not relevant. The units of frequency are not relevant. Compare the performance of P1 and P2. So the ideal CPI is 1 plus 0.5 ratio of loads. 50% of the load instructions suffer from a load use hazard. Isn't the fraction given over here? So there's clock cycle penalty of 1 here and clock cycle penalty of 2 over here. So this program has 0.2 branches. So 20% of this program is just branches. And if they're taken, then it's 0.5, right? The penalty will only happen if the branches are taken, right? So %50 of the load instructions suffer from a load use hazard. And the 40% of the instructions are load instructions. Okay, so 40% are load instructions. Take 50% of those 40%. That's the stall ratio times stall penalty, right? The stall penalty is just 1, but the ratio is like 40% and 50%. And then there's another penalty over here. We have a penalty of 2. 20% of the code is just branches. But all of the branches won't cause a penalty. Only 50% of the branches will cause penalty, right? So this is the final equation. And then we get 1.4 at the end. And for program 2, it's 1.23. The performance of P1 can be expressed as F divided by CPI, which is equal to 1 divided by 1.4. Hence, P2 is faster than P1. Wait. Frequency of P2 is 1.5. The frequency of P1 is 1. So you're doing F divided by CPI, 1 divided by 1.4. And then over here, we're doing 1.5 divided by 1.23. Their frequency divided by their CPI. And P2 is faster. Has a higher performance value. Most of the time, we do not measure the performance of a processor with respect to one program. We consider a set of known benchmark programs and measure the performance of our processor with respect to all programs to get a consolidated figure. Most processor vendors typically summarize the performance of their processor with respect to SPEC benchmarks. SPEC stands for Standard Performance Evaluation Corporation. They distribute sorts of benchmarks for measuring, summarizing, and reporting the performance of processors and software systems. Computer architects typically use a SPEC CPU benchmark suite to measure the performance of a processor. SPEC CPU 2006 benchmarks have 2 types of programs: integer arithmetic benchmarks, SPEC int, and floating point benchmarks, SPEC FP. There are 12 SPEC int benchmarks that are written in C, C++. Benchmarks contain parts of the C compiler, gene sequences, AI engines, discrete event simulators, and XML processors. On similar lines, the SPEC FP suite contains 17 programs. These programs solve different problems in the domain of physics, chemistry, and biology. Most processor vendors typically compute a SPEC score, which is representative of the performance of the processor. The recommended procedure is to take the ratio of the time taken by a benchmark on the reference processor and the time taken by a benchmark on the given processor. The SPEC score is equal to the geometric mean of all the ratios. In computer architecture, when we report the mean relative performance, we typically use the geometric mean. By just reporting the average time of execution, we can use the arithmetic mean. Sometimes instead of reporting SPEC scores, we report the average number of instructions that we execute per second. And in this case, scientific programs, the average number of floating point operations per second. These metrics give us an indication of the speed of the processor or a system of processors. We typically use the following terms: kilo kips, kilo instructions per second. Pips is million instructions per second. Okay. Interrelationship between performance, the compiler architecture, and technology. Let us now summarize our discussion by looking at the relationships between performance, computer design, processor arithmetic, and manufacturing technology. Let us consider the performance equation again. Equation 10.14. Let us assume arbitrary units for performance and replace the proportional sign by an equality. F times IPC divided by number of instructions. If our final aim is to maximize performance, then we need to maximize the frequency in the IPC. Simultaneously, we need to minimize the number of dynamic instructions. There are three knobs that are under our control: that the processor architecture, manufacturing technology, and the compiler. There are three knobs that are under our control, namely the processor architecture, manufacturing technology, and the compiler. Note that we loosely use the term architecture. We use the term architecture to refer to the actual organization and design of the processor. However, in literature, the common use of the term architecture to refer to both the ISA, the design of a processor. Hence, we use the same terminology here. Let us look at each of our knobs in detail. By using smart compiler technology, we can reduce the number of dynamic instructions and also reduce the number of stalls. This will improve the IPC. Let us consider two examples, examples 144 and 145. Here we remove one stall cycle by reordering the add and load instructions. On similar lines, the compilers typically analyze hundreds of instructions and optimally reorder them to reduce stalls as much as possible. Reorder the following piece of code without violating the correctness of the program to reduce stalls. No, I mean we can put add. We can replace add and LD. No, wait. This is not even used. I mean, we can completely remove add, right? R1 gets overwritten. So what even is the point of this? We have a load use hazard here. Between the load and sub instruction, we can reorder the code as follows. Now we do not have a load use hazard. The logic of the program remains the same. Reorder the following piece of code. Assume delayed branches with 2 delay slots. Add, load, subtract, add branch to foo. So we switch add and load again because we need R4. And do we add nope instructions? Or branch to foo. And then well, I guess branch to foo takes up 1 cycle, right? So I guess that will eliminate the load use hazard. So what are we trying to do again? To maximize performance. We have designed an advanced architecture in this chapter by using pipelining. Note that the pipeline by itself does not increase performance. In fact, because of stalls, pipelining reduces the IPC of a program as compared to a single cycle processor. The main benefit of pipelining is that it allows us to run the processor at a higher frequency. The minimum cycle time reduces from Tmax for a single cycle pipeline to Tmax over K plus L for a K-stage pipeline machine. Since we complete the execution of a new instruction every cycle unless there are stalls, we can execute a set of instructions much faster on a pipeline machine. The instruction execution throughput is much higher. The main benefit of pipelining is that it allows us to run the processor at a higher frequency. By running the processor at a higher frequency, we can ensure a higher instruction throughput. Pipelining by itself reduces the IPC for a program as compared to a single cycle processor, also increases the time it takes to process any single instruction. Techniques such as delayed branches and forwarding help increase the IPC of a pipeline machine. We need to focus on increasing the performance of complex pipelines through a variety of techniques. The important point to note here is that architectural techniques affect both the frequency and the IPC. Via the number of pipeline stages. Manufacturing technology affects the speed of transistors and in turn the speed of combinational logic blocks and latches. Transistors are steadily getting smaller and faster. Consequently, the total algorithmic work, Tmax, and the latch delay, L, are also steadily reducing. Hence, it is possible to run processors at a higher frequency, leading to improvements in performance. Manufacturing technology exclusively affects the frequency at which we can run a processor. It does not have any effect on the IPC or the number of instructions. So, relationship between performance, the compiler, architecture, and technology. Wait, hold on. It's frequency divided by the CPI, right? Why is it this IPC? Note that the overall picture is not as simple as we described in this section. We need to consider power and complexity issues also. Typically, implementing a pipeline beyond 20 stages is very difficult because of the increase in complexity. Secondly, most modern processors have severe power and temperature constraints. This problem is known as the power wall. It is also not possible to ramp up the frequency because we cannot afford the increase in power consumption. As a thumb rule, power increases as the cube of frequency. Hence, increasing the frequency by 10% increases the power consumption by 30%, which is prohibitively large. Designers are thus increasingly avoiding deeply pipeline designers that run at a very high very high frequencies. Power and temperature issues. How long is this? I think I will leave this up to next stream. Okay, this chapter is quite long. 10 point. Yeah, I think I will read this next chapter. Next stream, I mean. And then I will end the stream here then. So anyways, I will see you guys next time. Bye bye.